Today's lesson is on identifying quadratic functions. Previously, we've mostly been working with linear functions, so we've been able to identify whether or not something was a line based on a graph, an equation, a table, or a set of ordered pairs. Now you've got to be able to identify if, instead of being a line, that function possibly represents a quadratic function. So one major difference so far is that in a table, usually if it was a linear function, we would simply look at the changes in y and the changes in x and see if we had the same ratio between each change in y and change in x. So we would find the changes in y and we would divide them by the changes in x and see if they all reduce to the same number. That was for a line. So for example, if I were checking this table, I would have 1 divided by 1, which is 1, 3 divided by 1, which is 3, so the slope is not the same. So I know that this table doesn't represent a linear relationship. To check and see if it is identifying a quadratic function, I need to see if there are second differences that are constant only on the y coordinates. So the x coordinates, once you find the first differences, you're done. You don't need to go any further than that. You would first find the first differences in the y. So from 0 to 1 it went up 1, 1 to 4 it went up 3, 4 to 9 it went up 5, 9 to 16 it went up 7, but then you need to find the differences between the differences. So we call those second differences. From 1 to 3 it went up 2. From 3 to 5 it went up 2, and from 5 to 7 it went up 2. On your y coordinates, if you have constant second differences all over a constant first difference in your x's, you have a quadratic function. So the big difference here is that if it was linear, it would have been a constant ratio of the change in y divided by change in x, just with the first differences. With quadratic, you have to take the y coordinates and go a step further and see if they have constant second differences. So we'll do an example together. So determine if this following table represents a quadratic function. So first I'm going to look at the changes in the x's and just figure out the differences. From -4 to -2, it's going up 2. Again, it goes up 2, up 2. It happens to have the same pattern here the whole time. So when I look at y's, from 8 to 2, it's going down 6. From 2 to 0, it goes down 2. From 0 to 2, it goes up 2. And from 2 to 8, it goes up 6. So this is clearly not a line, because when I divide these changes in y by changes in x, they don't reduce to the same number. So now I have to find these second differences. So these were the first differences. Now I need to find the second differences. So from -6 to -2, you add 4. -2 to +2, you add 4. 2 to 6, you add 4. So because I have a constant difference in the x's, and I have a constant second difference in the y's, this is a quadratic function. From a graph, we have already spent time labeling different types of polynomials, and we should know that in order for something to be labeled quadratic, it has to have the highest exponent of 2. So if I have something like x to the 4th power plus x cubed plus 2x squared plus 5, because the highest exponent's not 2, it's 4, this cannot be considered quadratic. The highest exponent has to be a 2. So no matter how it's rearranged, if I can put it in standard form of order from greatest to least, and the highest degree, the highest exponent here is 2, then it's quadratic. If not, then it is not quadratic. So this first equation, it's already in a y equals format. There's no rearranging to do. The highest exponent on x is a 1, and if you remember from our labels, this is a linear function, so it is not quadratic. So no. The second one, even if I were to rearrange it and get y by itself, and I would minus this 3x squared, don't really have to do that to see this, but if I have y equals -3x squared minus 4, and now it's in standard form here, the highest exponent on x is a 2, so this is considered quadratic. So from an equation, you're really just looking to see if the absolute highest exponent is a 2. The last one on a graph, obviously this is the easiest on a graph. If you have anything other than a parabola, which is a U shape, then it cannot be quadratic. You are looking for the parabola for it to be quadratic. If you are given a set of ordered pairs, you follow the same rules as a table, and in fact, if it makes you more comfortable, you can take the ordered pairs and put them into a table, but you're still looking to see if you have a constant second differences on the y.